Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how to write momentum equations for two-dimensional problems. And in the picture I've drawn, I've kind of assumed a worst-case scenario here. So I've got two different masses. So I'm going to call this one mass A and the blue guy here mass B. The velocity of mass A before the impact is this vector right here. And I'm going to call that VA1 for velocity mass A, picture 1. The velocity of the second mass, mass B, is this vector. I'm going to give that a name. I'm going to call that VB1 for velocity of mass B, picture 1. Right now, picture 2, that's this stuff, what's happening after the impact. So this is the velocity vector for mass A. It's in the second picture, so I'm going to call that VA2. Here is the velocity vector for mass B, and it's in picture 2, so I would call that VB2. So we always start momentum we always start impacts by looking at momentum. And since momentum is a vector concept, it can be applied by direction. So one equation we can write for this is this. We can write conservation of momentum in the x direction, and I'm going to go ahead and call right positive x direction. And when I look at my picture 1 here, right, I've got this velocity vector down and right, making an angle that I call theta here with the positive x-axis. Not the best theta I've ever drawn, but so the x component of that momentum would be, let's see, MAVA1, that's the hypotenuse of the momentum vector, times cosine theta would give me the x component of this guy's momentum. Positive because it points right. Now, mass B. If I take mass B times VB1, I have the hypotenuse of the momentum vector, and if I multiply that by cosine of this angle here that I call beta, I would get the x component of it. And because that vector also points right, that term is positive. Then I look to the right, this guy's momentum is going to be MAVA2. I want the x component, so I'm going to multiply that by cosine phi. And I'm running out of room, so I'll have to kind of come down here, plus this guy's momentum, which is going to be MBVB2, and I'm going to multiply that by cosine of the angle alpha. Now, I left a space here. We can put equality between these because as long as we consider both of these at the same time, the interactive force between them, or the impulsive forces between them, are internal and do not affect the net momentum of the system. So again, that's an important concept of momentum, and that's because of how we're defining our system. Now, if I knew 3 of these velocities and all 4 angles, we could go ahead and find an unknown velocity, but more typically there's usually more unknowns than that. Another equation we can write for this example is conservation of momentum in the y direction. I'm going to go ahead and call up positive. And what I'm going to do is take this guy's momentum vector, which is MAVA1. I'm going to multiply by sine theta to get the y component. And then I'm going to take note from my picture. If you look right here, this thing has the velocity vector has an x component to the right and a y component that's down. Because I'm dealing with y components right now and it's down, that momentum is going to be negative. Right? Plus this guy's momentum in the y direction, that's going to be MBVB1 sine beta, equals this guy's momentum, y direction, MAVA2 sine of what I called phi, plus this guy's y momentum, net momentum in the y direction. And again, I don't have room, I'll just have to put this down here. And I'm going to take note that points down, not up, so minus MBVB2 sine alpha. So there's our 2 momentum equations we can write for this system. If we had 2 unknowns, we could solve for those 2 unknowns. And if we had 3 unknowns, there's 2 possibilities. We're either kind of up a creek, or when we have 3 unknowns in a case like this, we would ask ourselves, is it reasonable to write a conservation of energy equation as well? Normally in impacts, energy is not conserved, but there are special cases where it is. When material is very, very hard, like billiard balls hitting one another, that's a good example. There's not much energy dissipated due to material deformation, deformation. But the atomic collisions, proton to proton interactions are like this too. Or in the case of the lab that we do, the little carts that we made collide together, the magnet to magnet collisions where energy is conserved. As far as your homework is concerned, if you see the word perfectly elastic, elastic is a collision where energy is conserved. So if we believed it's reasonable to write a kinetic energy equation, conservation, this is what it would look like. We would add up all the kinetic energy that's before our impact, which would be 1/2 ma va1 squared plus 1/2 mb vb1 squared. And then we would add up all the kinetic energies in our picture after the impact. 1/2 ma va2 squared plus 1/2 mb vb2 squared. And if we believe they're equal, we'd put that between them. So here's our three equations we can write for a two-dimensional momentum problem. Conservation of momentum in the x direction, conservation of momentum in the y direction. We can do that because momentum is a vector concept, so we can apply it by direction. And if reasonable, we can write a kinetic energy conservation. That's kind of worst case scenario for a two-dimensional impact. If you have more than three variables, you're up a creek, because those are the only equations we can write without looking at other concepts. Again, in a little more detail, we can look at what's called coefficient of restitution in a dynamics class. You have equations for that, and that has to do with how much the material deforms versus reforms after the impact. But in most college physics classes, this is about as detailed as we get. So have a great day.